You heard Alex speak about command and control in the way a typical economist would. We hates it. We hates it forever. Let's have a closer look. Command and control is also known as direct regulation, and calls that in his book calls it prescriptive instruments. It is the most common form of environmental regulation, or probably regulation per se, and it reflects regulation as a lawyer would do it, or more relevant for environmental issues, as a natural scientist, a chemist, or a biologist, or a physicist would regulate this, because this is the logical thing that comes to their mind. If something is not right, then we must step in and forbid it. That's how these people think. Another reason why it is so common is that it was highly successful in the past. In the 60s and the 70s, Europe and North America were dirty, and it was cleaned up in the 70s and 80s, mostly through direct regulation by the government stepping in and telling people what to do and what not to do. And that was highly successful, and the people who were junior environmental policymakers at that time are now senior environmental policymakers, and they look back at the start of their career and say, how did this work then? Why would it not work now, even though the nature of environmental pollution has changed quite considerably? Essentially, what command and control of direct regulation does is that it prescribes aspects of the production process. It says, these are the inputs you can use, these are the inputs you can't use, these are the technologies that you can use, and these are the outputs you may produce. In order for that to work well, the government must know, the regulator must know what is going on. Essentially, it is a sort of one-size-fits-all type of regulation, because those are the only types of regulation that are allowed and that are feasible. Bill goes through Parliament, then essentially it applies to everybody in the same way. So it's always a one-size-fits-all solution, and one-size-fits-all is fine in two cases. First, the regulator knows the size of things, and second, everybody is roughly the same size. So if all pollution comes from a very similar application of very similar technologies, then you can imagine that the regulator knows how to solve this, or can acquire the knowledge to solve this. So this would be the case if you're regulating the 5 nuclear power plants that are in your country. Then you can imagine, and they're all using the same technology, then may all be owned by the same company, then you can imagine that the regulator knows or can acquire the knowledge to properly regulate things. But if the source of pollution is 1 million farmers doing slightly different things, then it's much harder to imagine that a regulator would actually know what to do and can come up with a regulation that applies to all farmers, because they're different, and the same is true for household energy use, transportation, and so on and so forth. There are just so many actors involved doing so very different things that it's very difficult to come up with a regulation that just makes sense to everybody. What types of direct regulation are there? Well, they come in all sorts of different guises. You can regulate the inputs, and one example is fuel efficiency. If your car does not get enough miles to the gallon or kilometers per liter of diesel or petrol that you put in your car and in your truck, then be it in North America or in Europe or in Japan, you simply cannot sell that type of car. So that is a regulation on the input. You can also regulate the technology that is used in the product. And for instance, it is forbidden, say in the automotive industry, it is forbidden to drive a car that does not have a catalytic converter. A catalytic converter takes out a lot of the precursors that cause acid rain. That is an example of a direct regulation of the technology. You can also regulate the output, and that can be the product characteristics. For instance, in Europe, you cannot sell toys that have paint on it that causes cancer if you eat it, and you cannot sell those toys if they are for children that are 3 years or younger. And the reason is that children tend to eat everything, and if they eat this paint, it causes cancer. We don't want our kids to have cancer, and therefore those products are simply forbidden. You can also regulate waste. Again, a European example, if you have a power plant, you cannot emit more than a certain amount of sulfur from your smokestack. That is a regulation. It's the output rather the waste product of your production. Those are common types of direct regulation. You can also regulate the timing of certain activities. For instance, in many airports, you cannot take off before 6 in the morning. That is to reduce noise around the airport. In some airports, you also cannot land after 11 at night. You can regulate things based on their location. For instance, in nature reserves, there's limits to hunting, there's limits to building, there's limits to chopping down trees, and so on and so forth. Things that are perfectly allowed outside a nature reserve are not allowed inside the nature reserve. And then you can go finally for total prohibition. For instance, chlorofluorocarbons, CFCs, the stuff that causes a hole in the ozone layer. You cannot make them, you cannot sell them, you cannot use them, and you cannot buy them either. All those things are simply forbidden. So those are the sort of direct regulations that we can think of. Now, Alex also said that these things are rarely efficient, and really what he meant to say that these things are rarely cost effective. And cost effectiveness was one of the criteria by which we wanted to evaluate our policy instruments. So what do we mean by cost effective? Well, cost effective is essentially that you want to meet your target at the lowest possible cost. So let's assume that we have n different polluters, and we give them the subscript n to make a distinction between them, and the costs of emission reduction follow this function where m is the emission reduction, and we assume that this is a simple quadratic form. So we have a linear term, beta m n, and then a quadratic term 1/2 times gamma times m squared. And cost effectiveness means that we want to meet the target, and our target is the total emission reduction, so the sum over all companies of their individual emission reduction should be greater than or equal than our target m without a subscript. So that is our target that we want to meet, and then we want to meet it at the lowest possible cost, so we want to minimize the sum of emission reduction over all companies, and of course subject to the constraint that we meet our target. This is constraint optimization, so we form the Lagrangian, which is the objective function, plus the constraint rewritten as an equality times the shadow price of that constraint, and that is given here by a lambda. So that is the Lagrangian, and then the first order condition for cost effectiveness is that the first partial derivative of the Lagrangian to the thing that we want to change, namely how much should each polluter reduce their emissions, so that's the LDM n should equal 0, the LDMN, and that is why we have a quadratic form here, right, so that the derivation is easy. So beta m derived to m becomes beta, and 1/2 gamma m squared becomes gamma mn. That's what the half is here. So this is the first partial derivative of the cost, and this is the first partial derivative of the constraint. So m does not depend on mn. This is just summation of over all mn. So for every little n that doesn't equal n, this becomes 0, and for the mn that is for the n that equals n, this becomes 1. So this is simple lambda, and this should equal 0. Or differently, the marginal cost, and I change notation here, the subscript here denotes the first partial derivative, should equal lambda, and this is true for all polluters n. Now, the insight here is that the shadow price of the constraint, the shadow price of our target, does not depend on which company, which polluter we're talking about, which household we're talking about. It's the same for everybody. The marginal cost of emission reduction should equal a constant that is the same for everybody. Marginal cost should be equal for all polluters. That is the way to reach your target at the lowest possible cost. The first to point this out was Bill Moll, who you see pictured here. And it's a simple equimarginal principle, right? Lowest cost of meeting your target is that everybody pays the same at the margin. Now, an implication of all this is that if the marginal costs are equal to everybody, then the actual emission reduction for company N equals, and that just follows from solving this again, lambda minus the cost, the linear cost divided by the quadratic cost. And these two things, this thing is the same for everybody, but this parameter and this parameter are different for every polluter, which implies that the emission reduction target Mn is different for every polluter. That is the implication of cost effectiveness. If different companies have different cost structures in terms of emission reduction, then everybody should have an individual emission reduction target. It's not one size fits all. No, the implication of cost effectiveness is that everybody has their own unique emission reduction target. And that is what makes it so very hard to reach this through direct regulation. Because it's much easier to say everybody should reduce emissions by 10%, or everybody should reduce emissions by 10 tons. That is a simple regulation or law that can be passed, but it's very hard to come up with a specific target for everybody, because you don't know what those targets should be, because the beta and the gamma are typically private information, so the regulator would not know. And even if the regulator would know, it's very hard to pass a law that says company A should do X, and company B should do Y, and company C should do W, and company D should do Z. That is very hard, if not illegal, to get through Parliament. Now, what does this imply for the distribution of costs? This is our first order condition for optimality, cost effectiveness, I should say. This is the implication for optimal emission reduction for company N. This was our cost function, so if we plug the solution into the cost function, we get this expression here. And that points to a number of things. So let's make this just a little bit more concrete. Assume that we have two companies only, A and B, and for both companies the beta, the linear parameter is 1, but for company A, the gamma, essentially how important is the quadratic term, is 1, and for company B it is 10. Now, if you go for equal emission reduction, both should do 1, then this is their emission reduction. Then the costs for company A are 1.5 and for company B is 6, so the total cost is 7, the total emission reduction is 2. We can also go for equal marginal costs, maintaining the same target of 2. Then company 1 should do much more because they have a much shallower emission reduction cost curve, and company B should do less. The total is still 2. Because company A does more, its costs rise, but because company B does less, its costs fall. And total costs are much lower, 3.82 rather than 7.5. So yes, equal marginal cost reduces the social cost, the total cost in this case, but the distribution of cost is very different, right? The company with the least cost, with the shallow emission reduction cost curve, should do more, and the one with the steep cost curve should do less. So there is a redistribution of cost going on, and the implication of this is, of course, that company A will lobby for equal marginal. No, it's wrong here. Company A will lobby for equal reduction, and company B will lobby for equal marginal costs. And then the question is, of course, which of the two is more influential, which of the two will work harder at lobbying. And you can immediately see that there's actually more at stake here for company A, so that company will tend to lobby harder. So firms fare differently on the different regulations and may lobby for the one that favors them. So that is an important thing to keep in mind here. Bureaucrats may not be neutral either. Some regulations are easy and cheap to implement, which you may think is a good thing, and if you were a social planner, you would say that is a good thing, but other regulations are hard to implement and expensive, and you may think that is a bad thing, but if you are a bureaucrat, and actually the more complicated regulation may actually be the one that you favor because it means more work for you, a larger budget for you. In the design phase, you need to hire more consultants and more lawyers to do the evaluation and draft the legislation. So that increases your budget and your importance in your organization. And also, then the implementation phase, if it's more complicated, you need to hire more people to actually look at all the forms and look at all the data and see whether people comply and so on and so forth. So more complicated administration actually favors the bureaucracy, and that is one of the reasons why bureaucracies tend to overcomplicate things. This is, of course, what Bill Niskanen, and you see him pictured here, predicted how bureaucrats would behave. There's another aspect here, and that is the locus of control. If you are the Ministry for the Environment, or the Department for the Environment, then a lot of direct regulation is done in-house. If instead you ask for a tax, then the tax is actually implemented by the Treasury or the Department of Finance. And that means that if you propose a tax, you actually lose control over the regulation, and it shifts to another part of the government. And that is why environmental departments tend to resist these sort of things. They much rather do direct regulation because that is in-house. And complicating things and keeping things in control is in the self-interest of the policymakers in this case. These things are not. These things happen, and they happen quite a lot. Here's an example from the UK, the climate change levy. The climate change levy is a tax to reduce greenhouse gas emissions, particularly carbon dioxide emissions. The climate change levy on power generation is 0.8 pence per kilowatt hour, which translates into 2.85 kilo, or the emission intensity is 0.285 kilograms per kilowatt hour. So the implicit carbon tax is £2.41 per ton of CO2. The climate change levy on gas is 0.003 pounds per kilowatt hour. Emission intensity is 0.028 rather than 0.28, which implies that the carbon tax is only 10 pence per ton of CO2. So you immediately see that this climate change levy violates the equi-marginal principle. The costs at the margin are different. But the gas levy has two exemptions. One is it is a lot lower. It's only 0.00075 pounds per kilowatt hour. That's 1/5. So you get 80% of the levy waived if you as a company have a climate change agreement with DEFRA, the department that implements this. Now this is strange, right? So the tax is not uniform, and you can get an exemption on the tax if you enter into a contract with the government. It's of course a lot of work for the government to check and negotiate and so on and so forth. So that is one exemption. There is another exemption, namely if the gas is used to generate heat and power, electricity, that is, and if you then have a combined heat and power plant, the same is true. There's very little gas that is burned just for heat on an industrial scale. You also get a 10% reduction on your climate change levy, and then the implicit carbon tax falls to 9p per ton of CO2. So this is quite complicated, and this seems to be one interpretation here is that this just increases, maximizes the amount of paperwork that the government has to process. That is, it maximizes the number of bureaucrats working on climate policy, and particularly this element here actually stimulates this. It actually rewards companies for making their emission reduction deviate from the general principle. I hasten to add that the large plants that burn gas are also subject to European regulations, also are part of the European system for tradable permits for CO2 emissions, which makes that small plants face this particular price, whereas larger plants face this price plus the going permit price, which is now something like 25 pounds per ton of CO2. So the principle that costs should be equal at the margin are violated here, and violated quite strongly. It's not even close, right? 2.41, 0.1, 0.02, 0.009, except when you're large, then it becomes 25. And that's quite a big difference. And also, particularly this part here seems to be designed to maximize the number of civil servants working on this.